There's a place 55 million light years away where even light, the fastest thing in the universe, checks in and never checks out. So what is a black hole really? We're going to answer that 3 times. For a curious kid, a high schooler, and a physicist. Same black hole, 3 levels. Throw a ball straight up and it always comes back down. That's gravity, the pull that holds you to the ground. Throw it harder, it goes higher. But what if you threw it so hard it never came back? It would sail off into space forever. A black hole is something so heavy, squeezed into such a tiny space, that its pull is monstrously strong. To get away from it, you'd have to move faster than light, and nothing moves faster than light. So nothing escapes, not even light itself. That's why it looks black. No light can bounce off it and come back to your eyes. Every black hole has an edge. Scientists call it the point of no return. Outside it, you're fine. Cross it, and you can never come back. So where do those come from? Mostly from giant stars. A star is a giant fire pushing outward, but when it runs out of fuel, there's nothing left to push back, and gravity wins. The star collapses into a tiny point, and a black hole is born. So, simply, a black hole is the heaviest kind of thing there is, with a one-way door. Whatever goes in, stays in. Every world in the universe has an escape price, a speed you have to hit to leave it and never fall back. For Earth, that price is about 11 kilometers per second. We call it escape velocity. Hit it and you break free. Miss it and you fall back. Escape velocity depends on 2 things: how much mass is pulling and how tightly it's packed. Pack more mass into less space and it climbs. On Earth, 11 kilometers per second. On a neutron star, which is a sun crushed into a city-sized ball, about half the speed of light. Squeeze further and you reach the point where escape velocity equals the speed of light itself. That's a black hole. The boundary where you'd need to beat light to escape is the event horizon, and the more mass, the bigger it gets. Now let me kill 2 myths. 1, a black hole is not a cosmic vacuum cleaner. Swap our sun for a black hole of the exact same mass, and Earth wouldn't get sucked in. We'd keep orbiting in the cold and dark, exactly as before. Gravity only cares about mass and distance, and neither changed. 2, that famous photo isn't the black hole. The black hole is invisible. What glows is the accretion disk, gas spiraling in, crushed and heated until it shines white hot, bright enough to outshine whole galaxies. The dark center is the shadow, where light fell past the point of no return. And if you fell in, gravity would pull your feet far harder than your head and stretch you into a noodle. Physicists genuinely call it spaghettification. So a black hole is just gravity, ordinary gravity, pushed to an extreme in a space so small that light itself isn't fast enough to leave. But honestly, gravity pulling really hard is not the full explanation. What a black hole actually is stranger than that. For that, we go to level 3. In school, we all learned that gravity is a force, a pull between things. Einstein's great discovery is that it isn't. Gravity is geometry. Mass and energy bend the fabric of spacetime, and what we feel as gravity is just things following the straightest path through that curved geometry. A planet doesn't get pulled by the sun. It coasts in a straight line through curved space. A black hole is that curvature taken to the breaking point. Solve Einstein's equations for a simple, non-spinning mass, the Schwarzschild solution, and one radius falls out. Rs equals 2gm over c squared, the event horizon. Here's what breaks intuition. Far from the hole, you can move toward it or away. Space is space, time is time. But cross the horizon and the mathematics swap them. The inward direction becomes time-like. Falling toward the center stops being a choice and becomes your future, as unavoidable as next Tuesday. The singularity isn't a place ahead of you in space, it's a moment ahead of you in time. At the center, the equations scream infinity, infinite density, infinite curvature, but infinity is physics telling you your theory has broken. Relativity stops working there. To go deeper, we'd need a quantum theory of gravity we don't yet have. And then in 1974, Stephen Hawking set quantum mechanics next to the horizon and found something staggering. Black holes aren't perfectly black. The horizon glows, faintly, thermally, and across unimaginable time. A black hole evaporates. Smaller ones are hotter and die faster. The temperature runs inversely with the mass. That one result tied gravity, quantum mechanics, and thermodynamics together, because a temperature means entropy, and a black hole's entropy scales with the area of its horizon, not its volume. It is the most entropy the universe lets you pack into any region of space, which leaves one of the deepest open questions in physics. If a black hole swallows information and then evaporates into featureless radiation, where did the information go? It's called the information paradox, and it is unsolved to this day. Same black hole, 3 levels. Beginner level, something so heavy nothing escapes, not even light. Intermediate level, gravity so strong that escape velocity beats light. Advanced level, curved spacetime with a future you can't avoid and a quantum glow nobody fully understands. Every explanation is just different depths of the same idea. That's Lumen levels. If this rewired something, subscribe and tell me what to explain next.